So now we'll discuss asymptotic order of growth. So I said you cannot associate any unit or any constant for runtime of the algorithm. Instead, you are expressing that as function of n, right? So what is the objective of using this asymptotic notation here is to compare and rank the order of the growth of an algorithm. You are using this asymptotic notation. What do you call that as? Asymptotic notation. So why do you require to use this? So computer scientists and mathematicians use this asymptotic notation in order to compare and rank the order of the algorithm. There are three notations I'm using here. The first one is big O of Gn. So this contains class of functions, that is Tn, that has got the smaller order of growth compared to Gn. So all set of all functions which is having smaller order of growth compared to Gn is classified into big O of Gn. Similarly, theta. When do you use theta notation? So whenever you have a algorithm whose runtime is say Tn, if it is having the same order of growth compared to Gn, then you are classifying that into theta of Gn. And if the order of growth of the program is Tn, and that is compared with Gn, if it is having the larger order of growth compared to Gn, then you are classifying that, or you can say that Tn belong to omega of Gn. So there are three notations here: big O, theta, and omega. So big O, when do you use? So when the order of growth of this Tn is smaller compared to Gn, and when it is same order of growth compared to Gn, you are classifying into theta of Gn, and omega of Gn, that is when the order of growth is larger compared to Gn, you are saying that Tn belong to omega of Gn. So Gn is our standard. So what are the standard functions or basic efficiency classes you can use? Gn can be log n to base 2, or it can be n log n to base 2 n square n cube to power n factorial. Okay, you got the idea? So what is Gn? So Gn is not associated with any constant here. So am I saying 2 log n to base 2 or n plus 2n plus log n to base 2 plus 10? So I cannot write. So basic efficiency class can be one of these listed in this table. You got the idea? Yeah? Yes? Gn ಯಾವ್ಯಾವ್ದಾಗಿರ್ಬೋದು? It can be log n log n to base 2 n square n cube 2 power n factorial. Okay. Even if you want to introduce new like basic efficiency class, it can be n power 4 like that you can use. Okay, but not associated with some constant. That I'll tell you why you cannot associate any constant with the basic efficiency class, that we'll discuss later. So Cn here, I'm using these three functions here. The first one is Cn. So Cn will give you the count of the basic operation. Okay, and Gn is a simple function. So I said Gn can be any one of these functions. So Gn is a simple function if you want to compare this Tn along with Gn. Okay, Gn is compared with this function Gn. Gn can be any one of these things. Okay, then Tn is actual count. When you have performed or when you have executed the program, you are counting how many times the basic operation is performed, right? So then you have to associate, or you have to say to which efficiency class that algorithm is belonging to. So you will get the exact count. Based on the exact count, you can able to decide is the basic efficiency class is log n to base 2 or n log n to base 2 or n square, like that. So that is actually Tn. Time required to execute the program is nothing but Tn. Okay, so we'll go to the formal definition of big O. Look at here, C into Gn. Some constant, with some constant you are multiplying Gn. And Tn, So Tn, is it below this curve C into Gn? Howda? So what is the meaning of this? Is the order of growth is less than Gn? Is the order of growth of Tn, is it less than Gn?
Yes, ma'am.
Yes. Okay. And is it proportionally increasing? Look at here.
Yes.
Yes. Okay. So can I say it's approximately same as that of C into Gn, or it is having less order of growth compared to C into Gn? This Gn is having either same order of growth compared to C into Gn, or smaller order of growth compared to C into Gn. Isn't it?
Ma'am, they're increasing at the same rate.
Same, but it can be here also, right?
Yes,
It
ma'am.
is now whatever curve I have written, it is exactly closer to C into Gn, but it can be here also, right?
Yes, ma'am.
Okay. Now, so we'll define like this. So class a function Tn that grow no faster than Gn. So formally we will define, so it's not being changed. I have changed yesterday definition here because I'm using T here. So So Tn is said to be in big O of Gn, denoted as Tn belong to big O of Gn if order of growth of Fn is less than or equal to order of growth of Gn, that is there exists positive constant C and non-negative integer n naught such that Tn is less than or equal to C into Gn for every n greater than or equal to n naught. Okay, so look at here. Tn is less than or equal to C into Gn for every n greater than or equal to n naught. This is how you have to define asymptotic notation formally. A function Tn is said to be in big O of Gn if and only if there exists a positive constant C and non-negative integer n naught such that Tn is less than or equal to C into Gn for every n greater than or equal to n naught. Then you can say Tn belong to big O of Gn. So look at here, 10n. So 10n, is it having the smaller order of growth compared to big O of n square?
Yes, ma'am.
Yeah, so how do you express? Because if I want to say that 10n belong to big O of n square, I should express in this format. That is Tn should be less than or equal to C into Gn. Okay, so how do I express that? How do I express that? So what is C here and what is N naught? Look at here. From 0 to N naught, it doesn't matter to us. And what kind of constant you have to take? It should be non-negative integer. What do you mean by non-negative integer? So can it, like whatever input you are taking, is the input size, can I say minus 10, minus 3, minus 4, like that? Yes. Are you there in the class?
Ma'am, could you repeat? I didn't get it
Yeah,
properly.
yeah. Okay, so I say input size. Okay, that is input you are taking from the user, right? N value. So can the n value be minus 10? Can you accept minus 10 number of elements to the array?
No, ma'am.
Yeah. Can you accept minus 20 number of elements to the array?
Only positive.
Only positive, isn't it? Is it not logical? Okay, and here look at here, when we are defining the constant here, what kind of constant we are defining? It should be a positive constant and non-negative integer and not such that. That's the reason we are considering only the first quadrant. Am I considering the second quadrant here to do the
No,
analysis? No. You
no, ma'am.
got it. That too, from when onwards it matters to me? From n naught onwards, right? So because I don't know how the function will behave from 0 to n naught, but from n naught and onwards, this is true. What is true here? Tn will be always less than or equal to C into Gn. So now we'll see how we can express this 10n. Okay, I'm saying if this belongs to big O of n square, then how I can express in this way. Okay, look at here. 10n, we said this belong to, okay, big O of, okay, it's not writing here. Okay, I'll just 10n belong to big O of n square. Okay, big O of n square. Yeah. So this is nothing but, is it Tn? Is it Tn? Yeah.
Yes, ma'am.
Is it Gn? What is
Yes, ma'am.
Gn here? Gn is nothing but, is it
N
n
square.
square only?
Yes, ma'am.
Yeah. Tn, is it equal to 10 into n? Yes?
Yes, ma'am.
Yeah. Okay. Now, how do I express this? I should express in this way. Tn must be less than or equal to C into Gn for all n greater than or equal to n naught. Howda? So you have to identify this C and you have to identify this n naught. Okay. Now, okay. Yeah. 10n, sorry, this 10n is less than or equal to, okay, so n square, what is the function I have identified, with what I'm comparing, what is my basic efficiency class here, which one I am using here? Well,
N square.
n square, that is Gn. Gn, this is the, to compare my algorithm time. So which is the standard I'm using? N square. That is nothing but, in general we'll call that as Gn. How the? So okay, now if it is 11, okay, if I consider 11, or if I consider, okay, no problem, 11 is also fine. Okay, I'll not consider 11. Instead of that, if I consider 2, okay, if I consider 2 here, okay, so from when onwards this condition will be true? Okay, what is n naught? How do you choose n naught here?
The one.
Is it 1? Look at here. 10 is less than or equal to 2. 10 is less than or equal to 2. Is
No,
it
ma'am.
true? No.
No.
Then, if it is 2, 3, 4, from when it satisfies? From 5 onwards?
Yes, ma'am.
Yeah. So what is, when you substitute 5 here, it's 50. 25 into 2, 50. Okay. So here it's equal to, right? 10n is equal to 2n square. Then when n equal to 6, this is 60. So 36 into 2, 72. From 5 onwards. So will this condition will be true?
Yes, ma'am.
That is, n is greater than or equal to 5. So since I can able to express in this way, Tn is less than or equal to C into Gn for all. Look at here. This is very, very important. For all n greater than or equal to n naught. That is for n, for all n greater than or equal to 5. Is this inequality holds good? You take any up to infinity. Will this inequality holds good?
Yes, it will be
Yeah.
true.
So, ನೀವೇನೇ ಇನ್ಪುಟ್ ಸೈಜ್ ಕೊಟ್ರು, Okay, so whatever may be the input size, it may be 10 power 6, it may be 10 power 20, it may be 10 power 100 or 10 power 200, 400, 500, whatever it may be. So from 5 onwards, this condition holds good. So with this, according to the formal definition, what is the formal definition says? A function Tn is said to be in big O of Gn if and only if there exists a positive constant C and non-negative integer n naught such that Tn is less than or equal to C into Gn for all n greater than or equal to n naught. If this condition holds good, what can I conclude? I can conclude that Tn belongs to big O of Gn. Is that right? Yeah, so with this, can I conclude in this problem? Okay, so can I conclude 10n belongs to, okay, big O of n square? Can I write like that? Bariboda? Yeah?
Yes, ma'am.
Yeah. Okay. So you got the definition? So in detail, I'll not do for the remaining definitions. Okay. You can write it by yourself. Okay. Now you got the idea of BICO. Okay. That is the function which is having the smaller order of growth compared to Gn. We are saying that as belonging to BICO of Gn. So contrast to this, there may be like Tn may be greater than Gn. Okay. So in that case, which notation will be using? Omega notation. That is, if Tn is having larger order of growth compared to Gn, then to which efficiency class you are classifying, sorry, to which asymptotic notation you are classifying it into? ಯಾವುದಕ್ಕೆ ಹಾಕ್ತೀರಾ? ಬಿಗ್ ಓನಲ್ಲಿ ಸ್ಮಾಲರು. ಓಕೆ, ಒಮೆಗಾ ಯೂಸ್ ಮಾಡಿದಾಗ ಈ ಕಂಡೀಷನ್ ಏನಾಗತ್ತೆ? What this condition will become? Tn will be having larger order of growth or smaller order of growth?
It will be greater or equal to.
Greater than or equal to C into Gn, right? Exactly. So now we'll see how to write the formal definition for omega of Gn. A function Tn is said to be in omega of Gn. This is denoted as Tn belong to omega of Gn if and only if there exists a positive constant C and non-negative integer n naught such that Tn is greater than or equal to C into Gn for all n greater than or equal to n naught. Look at the curve here. So is this Tn is above Gn?
Yes,
Yes?
ma'am.
Yeah. So that means, so any function which is above this, so will be classified into which efficiency class? Omega into Gn. You got it now? Yeah?
Yes, ma'am.
Yeah. So can I say now 10n square belong to omega of n square because it can be even it can be having same order of growth, right? And here n cube, can I classify it into n square? Yes. Look at here. So when I say log n, compare log n with n. Okay. So is log n is having smaller order of growth compared to n?
Yes, ma'am.
Yeah. So which notation I have to use in this case? Log n belong to big O of n or omega of n?
Big off and.
Very good, very good. Okay. So if I say like n, okay. So n is compared with n log n to base 2 or n log n to base 2 is compared with n. In this case, n log n to base 2, can I say this belong to big O of n or omega of n?
Omega of n.
Yeah, very good. That means, can I say this n factorial? Is it having the highest order of growth compared to all these functions?
Yes, ma'am.
Yeah. So can I say n factorial belong to omega of log n to base 2?
Yes, ma'am.
Omega of n?
Yes.
Omega of n log n to base 2?
Yes, ma'am.
Omega of n square?
Yes.
Omega of n cube?
Yes.
Omega of 2 power n.
Yes.
Yeah. So then what is n factorial here? Is it serving as a upper bound or lower bound?
Upper bound.
No, no. Uh, Look at here. When I say omega notation, you are exactly right. So how do you assess now? So because n factorial is the time complexity of the algorithm, we got it. I'm comparing with log n to base 2. I'm comparing with n. So this is serving as the lower bound, right? 2 power n. So when you are choosing the what basic efficiency class, you have to choose in such a way that at least it should be nearer to this. Can you able to gauge exactly what is the time complexity of the algorithm if you are choosing this way? N factorial is compared with log n to base 2. Can you able to make out?
Could be anything in between. So
Yeah, so it can be anything in between, right? So that's the reason most of the time we are not using omega or big O, because omega is serving as a, it is giving the lower bound or upper bound. Omega is
omega
lower.
is up, like if I compare n factorial with log n so n factorial is the upper bound.
ಅಲ್ಲಲ್ಲ ಇವಾಗ in general, in general you said the answer, now you are only reverting back. So is it a lower bound?
Yes, ma'am. Yes, ma'am.
Omega is a lower bound.
Yes, ma'am.
Yeah, so what about big O? Is
It
it
is the
serving as a upper bound?
yes, ma'am.
So can the order of the growth of the any algorithm, can it go beyond this?
No, ma'am.
No. So this is the upper bound for me. Okay. So whichever function you are taking here, whose like order of growth is less than or equal to c into gn. So gn is maximum here. Okay. It cannot go beyond this. So you are setting the upper bound. But if the my upper bound is say n factorial, assume that, and I'm using a function called log n. Log n is compared with n factorial. Okay. So log n to base 2 belong to big O of big O of n factorial. Look at here. That is the upper bound I'm using.
Yes, ma'am.
Yeah. So if I use, there's a meaning here. So if I use for this one, uh, sorting of to sorting the elements of the array, the upper bound is n square. That is meaningful because merge sort is having the efficiency n log n to base 2, and bubble sort is n square. So what is the upper bound here?
N square.
N square. Okay. So n log n to base 2. Can I say n log n to base 2 is less than or equal to
Yes,
some
ma'am.
c into n square? Yeah.
Yes,
So
ma'am.
can I say n log n to base 2 belongs to uh, big O of
Big O.
n square?
Yes, ma'am.
Yeah. So this is how you can make the comparison. Record ಆಗ್ತದೆ. Okay, so that is how you can make the comparison here. Okay, this is what the algorithm is. Look at the beauty of this. Now big O is serving as what? Upper bound or lower bound?
Upper bound.
Upper bound. Very good. Omega
Lower bound.
lower bound. Okay, so now because like if you want to assess exactly what may be the order of growth of the algorithm, better to use theta notation. In theta notation, uh, yeah, in theta notation, our formal definition here is a function Tn is said to be in theta of Tn if and only if there exist two positive constants C1 and C2 and non-negative integer n naught such that C2 into Gn less than or equal to Tn less than or equal to C1 into Gn for all n greater than or equal to n naught, then you can see that, yeah, Tn belongs to theta of Gn. Look at here. This Tn is bounded above and below by function Gn. In this case, I can say Tn belongs to big of Gn. Got the idea?
Yes, ma'am.
Yeah. That's the reason whenever you are the number of comparison is 10 n square, I can say straight away 10 n square belongs to theta of n square, right? Yeah. So that means what? It's quadratic in nature, right? So approximately how many number of comparisons will be made if input size is say 10? So if it is n square, so how many number of comparisons will be made?
Order of n square, like
Yeah, n
big
square. That
theta.
is it quadratic growth or linear growth?
Um,
Quadratic, right?
exponential,
Yeah.
like,
Okay, 10 andre 100. If it is 100, if the input size is 100, then
uh,
how many times basic operation will be performed? Is it 100 square?
yes, ma'am.
Yeah. So this is how it's going to happen. Okay, Napa? Yeah, you got the idea why we are measuring or why we are using asymptotic notation here?
Yes, ma'am.
Yeah. So with big O notation, you can assess what may be the upper bound of that algorithm. With omega notation, you can assess the lower bound, but exactly order of growth can be assessed using which notation?
Big theta.
Which notation?
Big theta.
Theta notation. Okay. Yeah. So you got the idea. Now that is summarized. Whatever formal definitions I have given to you, it is being summarized with this diagram here. So GN is my like standard, right? Basic efficiency class here is GN. Okay. I am comparing the Tn with Gn. So all this here, above I have written here. That means order of growth of this function is same or larger. When it is here, it is having like functions will have the same order of growth compared to Gn, and here the functions will be having larger order of growth compared to Gn. So all this will be classified to which notation? Which asymptotic notation you can use?
Omega.
Omega, and the function which is having same order of growth compared to Gn will be classified into theta of Gn, and here you have smaller order of growth, so which can be classified into big O of Gn. This is how you can use three notations. Okay, uh, big O, theta, and omega. We are calling this as asymptotic notation. Basically, why do you require to use this asymptotic notation? Can you please tell me? Tell me the answer.
To calculate the complexity, like code complexity.
Not only that, you have to compare and rank the order of growth of the algorithm. So you know that algorithm efficiency of bubble sort is, what is that? Big O of n square or theta of n square. But what about merge sort? Theta of n log n to 2, base 2. So which one is most efficient? The one which is having n log n to base 2. You know, like I have summarized in the table, right? So here it is being summarized. So n square is having higher order of growth, or n log n to base 2 is having higher order of growth.
N square.
So n square. So bubble sort is having n square, and merge sort is having n log n to base 2. So which one is most efficient?
N log n to base 2.
N log. Okay. So linear search is having the like number of comparison, or I can say that big O of n is the time complexity of linear search, and binary search is log n to base 2. So which one is most efficient? Binary search or linear search?
Binary search.
Yes, you got it now. ಏನ್ ಮಾಡ್ತಿದ್ದೀರಾ basically here? You are comparing and you are ranking the order of growth of the algorithm. Okay, so compare ಮಾಡಿ rank ಮಾಡ್ತಿದ್ದೀರಾ. Which one is most efficient? You can able to assess with this asymptotic notation. That is the basic idea behind asymptotic notation. ಅರ್ಥ ಆಯ್ತಾ ಅಲ್ವಾ? I cannot every time count how many times basic operation is performed. Instead of that, I'm expressing this as a function of n, and I'm assessing. So what is the approximately, what is the number of times you are required to do the basic operations? Okay, that is expressed as function of n, and that we are comparing with this basic efficiency class. Okay, with that I'll come to know which one is most efficient algorithm. Okay, so this is how we are saying merge sort is most efficient compared to bubble sort and selection sort. You got the idea now?
Yes,
Yeah.
ma'am.
Yeah. Okay.
Yes, ma'am.
So now here, this algorithm proof is not required. Anyway, it's very simple also. You can learn by yourself. So in this algorithm, what he says is if T1 belong to big O of G1 of n and T2 belong to big O of G2n, then T1 plus T1n plus T2n belong to big O of maximum of G1n comma G2n. Okay, that is two functions are there. So whichever is having higher order of growth, then this T1n plus T2n will belong to maximum of these two functions. So this is true for both omega and theta also. So for example, if I say 5n square plus 3n log n2 base 2 is there. So if I use n log n to base 2 here and n square is there, which is having the higher order of growth, is it n square or n log n to base 2?
N square.
N square. So obviously what we are trying to say that here is, so if you assume that there is an algorithm which will have two parts, one is having the efficiency 5n square, other one is having the efficiency 3n log n to base 2, then the algorithm efficiency will belong to which efficiency part?
N
The
square.
one which is taking more time, isn't it? So one is n log n to base 2 is efficient, but other one is taking n square time. But overall efficiency of the algorithm will fall into what?
Maximum one like N square.
Yeah, which is least efficient part, isn't it? One which will take more time. Which is taking more time? This one, n square. You got the idea now? That is what this theorem will say. Okay, you know that when I say T1n belong to big O of G1n, then T1n is less than or equal to C1 into G1n for all n greater than or equal to n1. And similarly, if I say T2n is less than or equal to C2, sorry, when I say, you know, when the theorem is given, okay, so whatever left hand side is given, so first we'll see, formally define these things with the definition, and then I have to prove this then part, right? Okay, so what is given to you? Belong to T1n of n belong to big O of G1n. That indicates that T1n less than or equal to C1 into G1n for all n greater than or equal to n1. Can I write according to the definition? Can I write according to the definition? So what we
Yes.
are saying, yeah, already we have said here T1n belong to big O of G1n. Andre, what is the implication? T1n is less than or equal to, for some constant C1, okay, C1 into G1n for all n greater than or equal to n1. And here, since we are saying that T2n belong to big O of G2 of n, so I can say T2n less than or equal to C2 into G2 of n for all n greater than or equal to n2. And we are defining some constant C3 in such a way that C3 equal to C1 plus C2 and N3 equal to maximum of N1 comma N2. C1, T1n plus T2n is less than or equal to C3 into maximum of G1n into G2 comma G2n for all n greater than or equal to n. For all n greater than or equal to n3. So with that, can I say T1n plus T2n belong to big O of maximum of G1n into G2 of n? Yeah, can I write that as in this way? ಬರಿಬೋದಾಪ? ಬರಿಬಹುದಾ? ಯಾಕೆ ಅಂತ ಹೇಳ್ತೀನಿ. Okay, so you have 2 is, sorry, it will take time to write. 2 is less than or equal to 3. Okay. Okay. Is that right? What I have written is right or not?
Yes, ma'am.
So 5 is less than or equal to 5. Can I write like this?
Yes, ma'am.
Yeah. So is 2 plus 5, is it less than or equal to 2 into 5? Can I write like this?
Yes, ma'am.
That means in general, okay, if you have C1 less than or equal to C2 and C3 is less than or equal to C4, can I write it as C1 plus C3 is less than or equal to 2 into maximum of C2 comma C4 bariboda?
Yes, ma'am.
Yeah. So The same thing is applied here, there. So T1n less than or equal to C into Gn. Alvapa? That is what we are trying to say. T1n belong to big O of Gn na enanta baradvi navu. So T1n less than or equal to C1 into G1n, and since in the left hand side it's being given that, what is that, T2n belong to big O of G2n, then T1n plus T2n belong to big O of maximum of G1n comma G2n. So why maximum here? So from these two, which is the maximum here? In this example, it is 5, right? So when you multiply it by 2, so will this condition holds good? Yes?
Yes, ma'am.
Yeah. So is it true for any integer? Is this condition holds for any integer, any positive integer? Forget
Yes,
about,
ma'am.
because we are not considering negative integers, right? So when this condition holds good, obviously this is true for this also. That's why we are saying that T1n plus T2n less than or equal to C3 into maximum of G1n comma G2n. Okay. So if that is the case, I can say T1n plus T2n belong to big O of maximum of G1n comma G2n. That is the theorem. Don't worry about the proof part of it. So we'll see now here an algorithm. Assume that there is an algorithm you have written to uh, check the element uniqueness of the array, that is whether elements of the array are unique or not. So in that you have written two parts. The first part is you are applying sorting algorithm. The sorting algorithm is nothing but selection sort. Assume that you are applying selection sort here. Okay. So the number of like basic operation you are performing here is half n into n minus 1 that you have counted, and I have given demonstration also. So if the number of comparisons is half n into n minus 1, then can I say this belong to big O of n square, Amit? Yes?
Yes, ma'am.
Yeah. In the second part, once you have sorted the array, if there are duplicate elements, will it be there in consecutive locations? Yeah?
Yes, ma'am. Like
Yeah.
one after another.
Yeah. What is the maximum number of comparisons is required to check there exists a duplicate element or not? So
N
first
comparison.
with, yeah, first with second, second with third, third with fourth, isn't it? So because let me write in I scribe. So what we are doing here is the assume that already I have sorted the elements of the array now by using some algorithm, that is a selection sort or bubble sort. Okay, now already this is how this is looking like this. Only here it is being repeated. Okay, so first one will be compared with the second one, right? So one comparison, then second comparison, right? Then third, then fourth, then fifth. So how many elements are there in the array? 8 elements there?
Six
6.
elements.
How many comparisons you are doing here? Is it n minus 1 comparisons? Yeah?
Yes, ma'am.
Yeah. So that is 5 comparisons. Exactly. That is what you try to say, Amit. Yeah. So in general, okay, the case what I have taken is n value is 6 and the number of comparisons what we have made is 5 comparison. But in general, if there are n elements in the array, how many number of comparisons you will be making here? N minus 1 comparisons. Okay, that means, can I say that belong to big O of n? Yeah. What is the overall efficiency of the algorithm? Can you say, because this is taking less time, can I say efficiency of this algorithm is big O of n? Can I say like that?
No, ma'am.
No. So then it efficiency of the overall algorithm belong to the least efficient part. Which is the least efficient part here?
N
The
square.
first part, isn't it? So which is taking more time, big of n square time. That is, efficiency of this entire algorithm belong to big of maximum of n square comma n. You got the idea now? You got
Yes,
the
ma'am.
idea? Yeah,
Yes, ma'am.
this is how you can analyze the algorithm. Analysis of the algorithm is very, very important, and like so that you can learn how to write the efficient algorithm also you can learn. And based on this analyzing the algorithm, with that you will come to know like how I can write the efficient algorithm so that I can minimize the time required to execute the program, that you can learn. And with that, it evolved different design technique. Anyway, design technique is not there in your syllabus. That is different design technique. For example, greedy technique, dynamic programming, backtracking, branch and bound, all that. Why do you require to use different design technique? Why you are required to do different design technique in order to like find the solution? Because you can, with this you can optimize the time required to find the solution. Okay, so we are not like ready to do say n factorial computations, right? For example, in Dijkstra's algorithm, if I go with the brute force design technique, then I need to find out n minus 1 factorial computations. I need to perform n minus 1 factorial permutation. Okay, so is it that easy? As the number of cities increases, if the city is say 10, it is 9 factorial possible number of solutions will be there. And if it is say 100, 99 factorial you are required to find out. Is it that easy? If you are performing that many number of computations, so sometimes you may require astronomical like you are required to wait for say years together. Okay, by the time it will find the solution, so no one of us will be there, so next generation can find the solution. That is highly impossible. So for that kind of problem, that is one which is involving permutation object. Permutation object ಅಂತಂದ್ರೆ ಯಾವುದು? um, or combinatorial objects. Which are all combinatorial objects? That is, it can be permutation, it can be combination, or it can be subset. Because if the problem involving to find out number of subsets, so how many subsets are possible for a given set? Can you please tell me? If there are n elements in an array, if there are if there are n elements, we'll talk about the set. So 2, 3, 4, 5. So how many sets are possible for this
4
subset?
squared.
Yeah, 2 power 4, isn't
4.
it? Yeah. So in general, if there are n elements, that is coordinate of the set is n, then how many subsets are possible? 2 power n. Yeah. So, okay, the problem which is involving finding the subset, okay, also permutation or combination. You know what is permutation and combination? The permutation is nothing but arranging the elements, and combination is nothing but you are selecting. So if there are n elements, from that you are required to choose or objects, right? So that is what the combination is. The function which is involving permutation, combination and subset objects is called combinatorial problem. In that case, uh, the runtime will be in exponential or it will be in factorial, isn't it? So that kind of problem you are required to find the solution. So how you can find the optimal solution with less time is the big question. For that you are using many design techniques. So that is nothing but backtracking, branch and bound, or it can be greedy, or it can be dynamic programming. So all that design technique will be used in order to minimize the time required to find the solution. That is very interesting, but that is not there in the syllabus. But as and when I take that like topic, I'll tell you what kind of design technique we have adopted in order to write the algorithm. Okay, so with this I'll be like winding off this class.